Chapter 2, The Integers. Today, much as we take for granted the fact that there exists a number 0, denoted by 0, such that a plus 0 equals a, for any whole number a, we similarly take for granted that for any whole number a, there exists a unique number negative a, called the negative or opposite of a, so that a plus negative a equals 0. In a natural way, or so it seems to modern-day mathematicians, this easily introduces the concept of a negative number. However, history teaches us that the concept of negative numbers was not embraced wholeheartedly by mathematicians until somewhere around the 17th century. In his work Arithmetica, the Greek mathematician Diophantus, who some call the father of algebra, described the equation 4 equals 4x plus 20 as absurd. For how could one talk about an answer less than nothing? Girolamo Cardano, in his seminal work Ars Magna, referred to negative numbers as numeri ficti, while the German mathematician Michael Stifel referred to them as numeri absurdi. John Napier, the creator of logarithms, called negative numbers defectivi, and René Descartes, the creator of analytic geometry, labeled negative solutions of algebraic equations as false roots. On the other hand, there were mathematicians whose treatment of negative numbers resembled somewhat our modern notions of the properties held by negative numbers. The Indian mathematician Brahmagupta described arithmetical rules in terms of fortunes, positive number, and depths, negative numbers. Indeed, in his work Brahmafusta Siddhanta, he writes, "A fortune subtracted from 0 is a depth, which in modern notation would resemble 0 minus 4 equals negative 4. If you find the study of the integers somewhat difficult, do not be discouraged, as centuries of mathematicians have struggled mightily with the topic. With this thought in mind, let's begin the study of the integers." Section 2.1, An Introduction to the Integers. In this video, we will learn about the opposite or negative counterparts of whole numbers contained in the set of integers, and how to order integers, how to find the opposite of an opposite integer, the difference between positive and negative integers, the definition and how to find the absolute value of an integer, and some applications that benefit from the use of integers. As we saw in the introduction to the chapter, negative numbers have a rich and storied history. One of the earliest applications of negative numbers had to do with credits and debits. For example, if $5 represents a credit or profit, then negative $5 represents a debit or loss. Of course, the ancients had a different monetary system than ours, but you get the idea. Note that if a vendor experiences a profit of $5 on a sale, then a loss of negative $5 on a sale, the vendor breaks even. That is, the sum of $5 and negative $5 is 0. In much the same way, every whole number has an opposite or negative counterpart. The opposite or negative of a whole number. For every whole number a, there is a unique number negative a called the opposite or negative of a, such that a plus negative a equals 0. The opposite or negative of any whole number is easily located on the number line. Number line location. To locate the opposite or negative of any whole number, first locate the whole number on the number line. The opposite is the reflection of the whole number through the origin 0. Example 1. Locate the whole number 5 and its opposite, or negative, on the number line. Solution. Draw a number line, then plot the whole number 5 on the line as a shaded dot. To find its opposite, reflect the number 5 through the origin. This will be the location of the opposite negative of the whole number 5, which we indicate by the symbol negative 5. Note the symmetry. The whole number 5 is located 5 units to the right of 0. Its negative is located 5 units to the left of 0. Important pronunciation. The symbol negative 5 is pronounced in one of two ways. 1. Negative 5, or 2. The opposite of 5. In similar fashion, we can locate the opposite or negative of any whole number by reflecting the whole number through the origin, 0, which leads to the image shown in Figure 2.1. The collection of numbers arranged on the number line in Figure 2.1 extend indefinitely to the right, and because the numbers on the left are reflections to the origin, the numbers also extend indefinitely to the left. This collection of numbers is called the set of integers. The ... on each side indicates that the numbers continue on infinitely. For example, both 23,456 and negative 117,191 are elements of this set and are therefore integers. Ordering the integers. As we saw with the whole numbers, as you move to the right on the number line, the numbers get larger. As you move to the left, the numbers get smaller. Order on the number line. Let a and b be integers located on the number line so that the point representing the integer a lies to the left of the point representing the integer b. Then the integer a is less than the integer b, and we write a less than b. Alternatively, we can also say that the integer b is larger than the integer a and write b greater than a. Example 2. Arrange the integers 4, 0, negative 4, and negative 2 in order from smallest to largest. Solution. Place each of the numbers 4, 0, negative 4, and negative 2 as shaded dots on the number line. Thus, negative 4 is the smallest integer, negative 2 is the next largest, followed by 0, then 4. Arranging these numbers in order from smallest to largest, we have negative 4, negative 2, 0, and 4. Example 3. Replace each shaded box with less than symbol or greater than symbol, so the resulting inequality is a true statement. Solution. For the first case, locate negative 3 and 5 on the number line as shaded dots. Note that negative 3 lies to the left of 5, so negative 3 is less than 5. In the second case, locate negative 2 and negative 4 as shaded dots on the number line. Note that negative 2 lies to the right of negative 4, so negative 2 is greater than negative 4. Important observation. In example 3, note that the pointy end of the inequality symbol always points towards the smaller number. Opposites of opposites. We stated earlier that every integer has a unique number called its opposite or negative. Thus, the integer negative 5 is the opposite of the integer 5. Thus, we can say that the pair negative 5 and 5 are opposites. Each is the opposite of the other. Logically, this leads us to the conclusion that the opposite of negative 5 is 5. In symbols, we would write negative 5 equals 5. Opposites of opposites. Let a be an integer, then the opposite of a is a. In symbols, we write negative a equals a. Example 4. Simplify negative 13 and negative 119. Solution. The opposite of a number returns the original number, that is, negative 13 equals 13 and negative 119 equals 119. Positive and negative. We now define the terms positive integer and negative integer. Positive integer. If a is an integer that lies to the right of 0, the origin, on the number line, then a is a positive integer. This means that a is a positive integer if and only if a is greater than 0. Thus, 2, 5, and 117 are positive integers. Negative integer. If a is an integer that lies to the left of 0, the origin, on the number line, then a is a negative integer. This means that a is a negative integer if and only if a is less than 0. Thus, negative 4, negative 8, and negative 1,123 are negative integers. 0. The integer 0 is neither positive nor negative. Example 5. Classify each of the following numbers as negative, positive, or neither. Solution. Locate 4, negative 6, and 0 on the number line. Thus, 4 lies to the right of 0, that is, 4 is greater than 0, making 4 a positive integer. Negative 6 lies to the left of 0, that is, negative 6 less than 0, making negative 6 a negative integer. The number 0 is neutral. It is neither positive nor negative. Absolute value. The absolute value of an integer is defined as its distance from the origin. It is important to note that distance is always a non-negative quantity, not negative, i.e. distance is either positive or 0. As an example, we've shaded the integers -4 and 4 on a number line. The integer -4 is 4 units from 0. Because absolute value measures the distance from 0, the absolute value of -4 equals 4. The integer 4 is also 4 units from 0. Again, absolute value measures the distance from 0, so the absolute value of 4 is also 4. The distance is 4 in both cases. Let's look at another example. Example 6. Determine the value of each expression. A, the absolute value of -7, B, the absolute value of 3, and C, the absolute value of 0. Solution. The absolute value of any integer is equal to the distance that number is from the origin on the number line. Thus, the integer -7 is 7 units from the origin, hence the absolute value of -7 is 7. The integer 3 is 3 units from the origin, hence absolute value of 3 equals 3. C, the integer 0 is 0 units from the origin, hence absolute value of 0 equals 0. Example 7. Determine the value of each expression, A, negative and -8, and B, negative absolute value of -8. Solution. These are distinctly different problems. The opposite of -8 is 8. That is, negative and -8 equals 8. Negative the absolute value of -8 equals -8. Since the absolute value of -8 is 8, then the -8 is just -8, since the opposite of 8 is -8. Applications. There are a number of applications that benefit from the use of integers. Example 8. Profits and losses for the first 6 months of the fiscal year for a small business are shown in Table 2.1. Profits and losses are measured in thousands of dollars. A positive number represents a profit, while a negative number represents a loss. Create a bar graph representing the profits and losses for this small business for each month of the first half of the fiscal year. Solution. Start by labeling the horizontal axis with the months of the fiscal year. Once you've completed that task, scale the vertical axis to accommodate the profit or loss values recorded in Table 2.1. Finally, starting at the 0 level on the horizontal axis, sketch bar graphs having heights equal to the profit and loss for each month. Note that the bars in Figure 2.2 for the months January, February, March, and June have heights greater than 0, representing a profit in each of those months. The bars for the months April and May have heights that are less than 0, representing a loss for each of those months. Example 9. Table 2.2 contains the low temperature recordings, degrees Fahrenheit, on 5 consecutive days in Fairbanks, Alaska, 1995. Create a line graph for the data in Table 2.2. Solution. Start by labeling the horizontal axis with the days in January that the temperatures occurred. Scale the vertical axis to accommodate the temperatures given in Table 2.2. Finally, plot points on each day at a height that equals the temperature for that given day. Connect consecutive pairs of points with the line segments to produce the line graph shown in Figure 2.3. Note that the points in Figure 2.3 have heights greater than 0 for January 21 through January 23rd, representing temperatures greater than 0. The points representing January 24th through the 25th have negative heights, corresponding to the negative temperatures of 2.2.